Alright, so hopefully I'm live, and today we will do some experiments with 3458A multimeter, including teardown and some component replacements. Is the sound okay? How are we looking? Had some technical issues with the new setup here, but hopefully everything is fine now. Is the sound volume okay? All right. So the lab is looking a little bit different since the last video a long time ago, because I built a new bench. It's still work in progress. So it's using extrusion, aluminum extrusion profile, 45 by 45 beams, and the overall bench length is around 8 meters, actually 8.5, and it will support a lot of upcoming projects. So I have right now in the central section all the metrology toys are living there. So there is the shelf on top with the calibrators, two Fluke 5720A, amplifier on one of them, arbitrary generator in the right top corner, then have projects in progress in the middle, including the 8508 Fluke 8.5 digit repair project. Then we have little resistance station in here. So there is Datron 1281, WaveTech 4920M, Fluke 5450 resistance calibrator, reference divider, high resistance low current meter, Keysight B2987A. Then we have the temperature chamber, DUI box with the Peltier element, a cooler inside. Then we have our usual suspects, 3 Keysight 3458A and 2 Keithley 2002s. Then we have nanovoltmeter on the far edge over there, and some other auxiliary equipment. Our primary resistance standard, that white box in the background, ESI SR104, and some metrology grade cables. But today we'll be taking that 3458A number 11 on top, taking it apart, doing some replacements, and we'll see if it works as expected or we will have some issues. I expect a major fail, but we will see. So I'll have to take the meter out of there and put it on our surgery table, and we go from there. Hopefully the noise from the audio is not too much, because all the gear is running 24/7 to preserve the stability and accuracy. And this is Keithley, it's actually DUI box using Keithley 7001 mainframe with 2 nanovolt scanner cards. So I'll have to make some space, disconnect this probe. to pull it out. Don't forget to disconnect GPAB cables. This is my experimental DMM, so I got it specifically for the purpose of various experiments, and also to compare with two of my other meters that I maintain in calibration. So almost there. All right. So here is the meter. Let me relocate the camera. There we go. So it's original actually HP branded old meter, which I replaced the front panel, did some minor repairs, but there's still the push rod is broken, so I cannot put the cap for the power. But it's not a big problem. I rarely turn off the meters. So then on the rear we have our usual, let me see, probably will need to zoom in into closer in. Here I have connected rear outputs, so I think we need to remove this cable. I like to get it extra tight, so there we go. You can also see one of my typical hacks. I don't use the filter. Like usually there is a dust filter in front of the fan, but I don't install it on any of my meters to reduce the temperature for that half a degree or so. So I can get less worry about filter getting clogged and then need to remove the meter from the setup and clean it up and everything. So I just run the fan without filter. So we'll have to remove the top cover and get access to A1 board, and we go from there. I think this angle is pretty good. All right, so there is a, I believe this is, there is T15 screwdriver, so we'll need to remove the 4 screws in here to remove the bezel. Now we have, I think there are still 2 screws on the side. Yep, I need to just remove this one. This should do. Okay. Now the the cover just slides right off. Or can actually just hack it out. There we go. So we can see typical for any 3458A, old motherboard, and all the analog stuff is in shielded box. Main transformer. Many of the people who are interested in precision instruments already familiar with this side. So we will go ahead and remove the top cover. And see what's there. There we go. So this is completely standard, no any crazy modifications or anything. Very standard 3458A. Let me get the camera in the right angle. There is non-original in-guard board for power supply board, but it's completely identical to HP board. And here we see all the precision goodness. And today's question is that little module in the corner of the A1 PCB. That is primary DC voltage reference. Let me zoom in right there. So today the idea is to replace that board with something special and see if the meter still works and verify if actually we make it any better or completely break it, which is also a possibility because I didn't actually attempted stuff I'm going to show today before, so I have no idea, and we will see. So this A9 PCB is based around LTZ1000 voltage reference, which is the best money can buy on the market even today. And there is no much alternatives to replace it because there is no better reference chip. So what we'll do is replace it with the custom board that is right now sitting in that black box. So let me get it out of there and show you. So I'll use ESD strap for that. So there is something right there. I use the metal box just for testing purposes. So I'll just slide it out. All this wrap is to prevent airflow. So what we see inside, that is essentially 4 of the LTZ1000A voltage references. Oops, sorry about the angle, it's a little bit tricky. This is own custom design. It will be explained in better details on xdevs.com site, but for now I can tell this is essentially 4 references in same board. This is a 6-layer Rogers ceramical based PCB. So it have individual references modules, so you have 2 resistors op-amp, actually dual op-amp, some filtering cap, some passive components around, and then you have 1, 2, 3, 4 of them, and then they group together and provide single average output. So hopefully that reduces noise on the total 7-volt output, because the noise between each of the reference is not correlated, so it will be average by the passive resistor in here. That's a resistor network. And also you see 4 transistors. Those are heater transistors. They are also separate for each of the reference. So essentially I could assemble just one reference on the whole PCB and it would be still functional and providing 7-volt output. There is low noise regulator based on linear LT3045, and then also output buffer, which is not used right now in this configuration, but it's actually supported for alternative use if you implement 10-volt booster stage. And then on the back there is just a few thermal pads. We can remove them. These are really thick. And then there is no components on the back. Just gold-plated, pretty PCB with white solder mask. And all the exposed areas, this is just ground, so we don't worry about any electrical pickup from there. So you can see there are 2 connectors, 5-pin connectors on each side, and they are positioned and oriented precisely the same way as 4 connectors, those red ones, on A1 PCB. But it's not as trivial as just one-to-one replacement. We will have to do some butchery before we will be able to install it. Okay, let's get to it and remove these 2 screws. I just recently calibrated this 3458A, so essentially it was completely in 24-hour specifications against my 2 other 3458As and against my primary 10-volt standard and 10 kilo ohm standard, and all the transfers from Fluke 5700 series calibrator 5720. So there we go. Then the references just go right off. So you can see the plastic cap to prevent the airflow from the fan nearby, from instrument air intake, affecting the temperature stability of the reference and reducing the overall noise. And to confirm that this was just standard chip, resistor is 15 kilo ohm, 1 kilo ohm, 111 ohm, and then there is no low oven temperature modification on this reference, which would be 100 kilo ohm resistor placed in these 2 spots. So we can keep this reference in case we need to come back to it, and we'll try a test fit of our special module to see what we need to do to make it installed. I have a blank PCB, which we can just do as a trial. So here is the blank board. Probably this is a little bit overexposed. There we go. So you can see the board is much bigger than the original one, and there is some interference. So let me put it to the pins like it's supposed to go. You can see the pins sticking out right there. Probably I need to move to the macro lens. All right, let's do that. Here's my macro lens. Should see much better. So we can see pins sticking out. That says where is the connector located. But something else in this area preventing us to get the board down to its location. So if we remove, this is this selecting switch, which connects either ground or 0 or the 7 volt output from the reference to the bottom of the instrument, where is the ADC and everything else. So what we'll need to do is to remove this jumper and put a short right on the PCB, so we don't have this tall component sticking right there. And no, rear fuse holder is not, it's close, but it's not, there you have, probably better to change the angle a little. It's close, but not that close. And there you go. So there is some clearance in there, no problem. So one option we could do is to remove the whole A1 board, desolder this connector, rather jumper posts, and solder just a short in there. But that's kind of a lot of work, probably for 30 minutes or so. So what I'll do, I'll get a little bit medieval and, well, make some people cringe, that's for sure. So we can use the universal tool that fixes everything. You get the idea from now what is about to happen. And what about the idea installing the taller headers? Well, I still want to use the internal shield all over the board, so that wouldn't really work, because I still want to enclose the meter as it's supposed to be used and have it all contained. All right, now we will need to remove that plastic thing. It probably will not go easy on us. So let's see. Little gentle wiggle. Well, maybe not so gentle. Nope. Just a plastic piece, so if it's get damaged, I don't really care. But obviously I don't want to damage the board, because if you want to buy a replacement for this board, it will cost more than half of the new instrument. Well, maybe not half, but around close to 4,000, that's for sure. Okay, I think we're getting close. I don't recommend for anyone to do this. So don't try this at home. Oop. Some bits and pieces flying. There we go. So we will still need to restore the jumper position. Once we're done with this battery. Yep, almost going. Almost there. There we go. Okay, but we're not done yet. Okay, now it's much better. There is also this guy, this test point sticking out TP100. It's not tall enough, but it's kind of in the way. Let's see, where is it again? So it's right around there. There, so it's right around here. Yeah, I can just snip that point off. It's not that I'm going to use it for anything anyway. Shouldn't be a problem. There we go. Problem solved. No, you don't usually need hot air to desolder any caps. Actually, it would be even worse because hot air will also hit the cap, and if it's electrolytic cap, it can explode and you can be left without an eye if you get unlucky. So I would strongly advise against using hot air for removing capacitors, especially electrolytic capacitors of the PCB. So now that we have cleared the tall components, we can try to put the actual board and see how it fits. So first we'll need to desolder those couple test wires, the ones that come in from the bottom. Let's do that. So I'll just put a shield back on temporarily, so we don't have the solder pieces flying around. Probably would be better if I have some kind of black background, but I don't think I have anything like that. Yeah. Alright. There we go. Should be okay. So I need to remove all those jump wires. Let's get the fume extractor going. And we need a soldering iron. So good old ERSA Icon 1. So the temperature I'll need around 300 C. So you can see it's trust me, it's 300 will be soon enough. And then we can go ahead, remove the wires. This is just Icon 1, it's not Nano or Pico or anything, because I often solder on the multi-layer boards and I need every bit of power that solder iron can provide. In case of Icon 1, it's 120 watts, and I have a nice set of tips for all the kinds of worked types, including very thin and ending to the 10mm wide juicy tip for stuff like capacitor replacements. So let me remove this stuff. Okay. Now the output, the voltage reference output, is that white wire, plus and minus, so we don't need that anymore. There we go. Also there was a jumper, this jumper right here, because actually power provided for heater and power provided for the actual voltage reference power, completely separate electrically. So these jumper wires, for the testing purposes, they are shorting together, but in actual instrument they are maintained separate. Okay, I even put some small labels. They are really hard to see, but I can try to zoom in. And we need to clean up the board a little. Let's see if that's zooming. Yep, it's upside down. All the electrons will fall down. Oh. So the lines are, let me put it properly. There you have. So the first one, AG and D, ref out, ref return. This pin is not connected, T-sense, plus 18 volts heater, minus 15 volts, heater return plus 18 volts, and oven B, that's the test signal from the second cell. And then also some other test points. So this is for development and debug purposes. Each of the cell have separate plus and minus output. And then this bottom 4, this is the output from the active buffer. And then there was a question, what are those capacitors on the back? Well, I'll leave that question to our viewers. Why there are this black stuff, components soldered across, what we can see is precision resistors. They look like typical crystal, but they are not crystals. They are hermetically sealed V-shaped foil resistors. Very nice and pretty, and also very expensive. The stickers with the numbers, those have some meaning. So we'll see if the readers can figure out what that meaning is. So this is overall design. And all of these LTZ reference chips, they are not just random chips, they are selected. So it's very expensive board to make. The question is what I'm doing with such extreme equipment. Well, mostly I use it to educate myself about analog electronics, different design methodologies, and also precision measurements, because one of the ways to learn is to experiment and try different ideas in hardware and see if the theory matches the practical results, and if it does not, then learn from that and find out if it's either your error or is it shortcomings in design. So this is like a learning tool for me, like a practical lab examples where I can try different things. Depends on what is interesting for me for the moment. So this equipment does not earn any money other than just fun. I don't sell anything. And it's a fun hobby. And it's not that like I bought all of this equipment brand new for the extreme prices it's usually listed. Most of the equipment I bought completely broken, like many would say beyond economical repair, and just worked on it and repaired in the spare time. So whole this project and that equipment I showed in the beginning of the video, that took about 9 years to accumulate. So it's definitely not the hobby you would want if you need quick results. Okay, I think this board is nice and clean. So we can try to put it in and see how it fits. So that's our spot. not the cheapest hobby. Well, that depends, because you still can play with the precision measurements, even with the 6.5 digit multimeter, like Keysight or HP or Agilent 34401, which you can buy from eBay for maybe like $100 if you're lucky. So there is definitely applications for this hobby for any budget. It doesn't have to be that you can do a lot of stuff and a lot of interesting experiments with just 6.5 digit meter, even if it's old one, like for example 3456A, very capable multimeter, and you can buy one for good money on secondary market. So yeah, even using 6.5 digit meter is very educational when you start seeing that different components, they are not exactly perfect. All these variations from temperature, from voltage, from signal supplied, you can actually detect that with just 6.5 digit meter. Alright, so board is in place. I don't like that the connectors don't go all the way in. So still making contact, but it's a little bit how you're doing. And also I'm hitting these two test points with the back side, which is our ground, so that would be unfortunate. So these are test points are plus 18 and minus 10 volts. So we'll do our snip. So let's remove this cable for a second. Whoa. Let's hold it better. All right. There is also this test point TP401 and the transistor, so I can just bend the transistor down carefully like so and snip that point a little. And now the next tall part, something that we cannot remove, it is this precision resistor R310. So we'll have to make do without it. I mean, without doing anything to it. That is part of the resistance resistance current source circuitry. So it's kind of important to keep it there. Okay, it's much better now, I think. Yeah, let me look. I think it's okay. I can see the pins making good contact. Let's see that, yeah, we don't have any metal pieces protruding on the other side. I guess we can try to power on and see what happens. Maybe I can get a shot on that connector. Let me get the camera closer. Probably will be easier to just rotate the meter. Let's do that. board is not perfectly flat, but that's all right. So there we have. That's the connector, and I can wiggle, and you can see the pins from the board. They come in protruding from the bottom and touching those gold-plated contacts. So looks okay. Can also show some components around. This is protection for power. Those are operational amplifiers for each of the LTZ reference. As you can see, I don't use ADA 4522 chopper for this design. I like ADA 4522. It's actually right in here for the output stage. I'm not sure if you can see the label, but it's there. But it's not used for the LTZ reference itself. And this is output stage, it's not connected. And then the trim resistors, those R9, R10, R11 network. That's responsible for forming 10 volts. If we design this board for 10 volt output. Right now it's just outputting 7 volts average from each of those LTZ references, because that's how it's supposed to be in 3458A. Okay, so let's power on the meter and see what happens. I think for that I'll need to move meter back to the lab location where is all the other stuff. So we can connect to calibrator and do the quick calibration. So there is our calibrator, which we'll be using today. And let me clean up that spot. So I'll need to replace the lens again. Still use DSLR for the video, so it's kind of a little bit awkward and inconvenient, but that's okay. Yep, jumper is still open. I was waiting for somebody to notice, so yes, now we can solder the copper short instead of jumper and get back to the project. So why I was saying that this will probably be a big fail is there are actually two reasons. One of the reasons that this reference module taking 4 times more power than original A9, and that might be the problem, because if the other circuitry around these connections around this original A9 using those rails for power, there could be some voltage drop in ground, some voltage drop in the power rail, which could cause the problems and make the meter essentially not working correctly. So that is one of the reasons. And another reason is that the heat from quad LTZ reference board would be much bigger than just single board. So it would cause the thermal gradients all around these precision components in proximity. So that would be pretty bad for the stability, and probably will have large errors for the other functions as well. So there is a lot of potential for the failure. Let's say that. And regarding Fluke 5700A 5720, yes, there are two voltage references around linear LTFLU on the heated ceramic hybrid, but it's not as straightforward as just using two for their average. They actually depends on the function and depends on the operation mode of the calibrator. They are actually used as a 6-volt reference or 13-volt reference, or as a average together. So, and there are a lot of buffering and filtering and the whole thing, whole board of the stuff. So this design in here, this concept, is much simpler than what is implemented in 5700 series. What is BGA core swapping? Is it, do you mean the BGA chip replacement, like GPU or CPU or something? LTZ1000A is essentially same performance level as LTFLU. Some people argue LTFLU is a little bit better. Some people argue LTZ1000, but LTFLU is a little bit more difficult to use, and also you cannot buy it. You can try to get it from some second source dealers or some shoddy eBay sales, but usually you get the fakes or the chips that are rejected for whatever reason. But I don't want to spend a lot of time trying to find a good LTFLU and then spending even more time to design the circuit that works for a specific chip and then redo the trimming and adjusting for another sample again. So I just stick with LTZ1000. I can buy them and I'm familiar with the circuit, and it's fun to work, and also you can repeat the circuit, and anyone can repeat it because you can buy all these parts. They're expensive, yes, but you can buy them and order them even on DigiKey, so it's more accessible than some unobtainium stuff. Like, for example, I used a Fluke network resistor in my previous reference project, XDevsFX. So you cannot buy that resistor network, and you cannot repeat the design. You can do something similar using the standalone resistors, but it wouldn't be the same. So I'm just cleaning this piece of copper wire. Oops. So I can put the short in there instead of the jumper. And yes, LTFLU was a replacement for Motorola CZA263. It's not exactly one-to-one, but it's very similar. Using the same idea, same concept, and linear, and now linear is part of ADI, So Linear exclusively make LTFLU chips available for Fluke. So that's why you don't see LTFLU in any other vendor's instruments, because they are exclusively made by order from Fluke. And since the Fluke is now part of Fortive Group, as well as Tektronix and Keithley, you can find LTFLU in Keithley DMM 7510. Otherwise, Keithley would still be stuck with LTZ1000 like they do in Keithley 2002. I mean, nothing wrong with LTZ1000. I like them very much. So it's more like a designer preference rather than actual performance difference. I'll need to make the hole. Let's do a little zoom in. There we go. I often use this toothpick trick when working with through-hole PCB and PCB components. There is our short. Yes, that was just normal wooden toothpick. It fits the through-hole pins perfectly. I mean through-hole holes. This will be enough for a dozen of years. All right, so let's do it. Also, I'll have some cover over the LTZ chips. It will not be left like that if we can confirm that this is indeed have a chance to be working. All right, let's get on. So what we'll need to have is the spot where all those cables are. There we go. This is actually one of the transport cases for the calibration purposes when I was shipping my primary resistance standard. It's a very nice box. I wanted to have that extra bit of protection for the precision equipment. So here's our meter. We'll need the power cord. I think I'll need to a little bit longer power cord. Alright. So what I'll want to have is I'll power on the meter and measure the output voltage, because there is a third issue that would probably cause our experiment to fail, and we'll get to that in a second. But first I need to get my multimeter that is responsible to repairing and fixing all this fancy gear. Is good old trusty 87.5. Love this meter. So we will use it to measure the LTZ reference outputs, and also make sure that the power rails are all good. Connect the cable back in. So let's power on and see what happens. In the worst case, we will have one perfectly fine 3458A turned into a dead unit. It's not a big deal. Let's make sure no shorts, no nothing. Yeah, doesn't touch any metal surfaces. Should be alright. Or not. Okay, there is an error. And it doesn't work. So let's turn off for a second. Do a sniff test. I need to have a ground point. And do some checks. So yes, there is no LTZ voltage, it's 2.4 volts. That is not correct. So let's see our plus 18. It's minus what? Let me check the pin mapping. Probably I can connect back the original reference and make sure it's still everything works after our surgery. Or would I rather say butchery? Wrong way. Okay. Okay, meter works with the original reference. Let's connect 10 volts just to see that it indeed works. So 10 volts. Yep, that looks okay. pretty close to 10. So let's measure the signals according to the mapping. So this is supposed to be ground, and that's our reference, 7. And we have plus 18 right here. Okay, this is minus 15, which is really interesting, because that means that I made a mistake, and it's rather a big one. Oh boy. So the orientation of one of the connectors have wrong pins. Alright, let me explain that for a second. Yeah, rookie mistake. All this fancy expensive equipment, and we are still making silly mistakes like this. Let's see how difficult will it be to fix this error. But like I said, there was very high probability of failure. And I guess we proved that in practical example right now. So let me open the PCB file, and we can see exactly what's going on. And if we have a chance to resolve this without major exercise. So I need to open the file first. Give me a second. Well, that's a good to know. So let me get that. I think it would be a little bit tricky. Because, well, yeah, there is a connection on the inside layer, but I think it's still possible to rectify. Give me a second if I can switch the view. Захват. Okay, let me rescale the window. So the issue I'm talking about is, yeah, the middle pins. So how this is supposed to be, that this line is supposed to be plus 18 volts, and then other one, this one, is minus 15 volts. But this is how it's done on the meter. And then the middle one is heater ground, so that is fine. Let me redo the colors a little. And the corner is oven drive, it's not connected to anything. And then this one is high voltage, plus 18 volts for the heater. You can see it goes to those array of transistors. So right now we have, if I just connect board as is, I have this plus 15, plus 18 and minus 15 reversed. So right now we are looking at the top layer. So this is supposed to go inside layer, goes in here to the filter and goes to our regulator. That is fine. And this one connects to this LED, which is not populated, and the resistor, compensation resistor right in here. So we can see second layer. So this is the heater power, connects to the corner pin. Let's check that is correct. Let me switch there. So we're supposed to see 18 volts on the corner pin. No, it's not 18, so the whole connector is reversed. Okay. Well, that's fun. So what we'll need to do is to do a bunch of bodge wiring. Okay. So this green should be connected on the other end as well. There is no connection. This is the second layer. This is just ground. No connection here, no problem. This is power layer. No connection, no problem. This is layer number 5. So here we have just straight this VCC, supposed to be 18 volts, and then oven drive. So what we can do here, we'll need to break this pin open. It doesn't have actually to go to the DMM, I think. And then we will need to have, this is the bottom layer. So the only good pin is the middle one. But what I can do here, I can ignore this connection, because I have here on the top, it's just a capacitor, resistor for LED, and then the filter. So instead of the filter, I can connect to that output point with the jump wire to this. So this green pad will connect to this pink point, and then this resistor we can just tombstone and connect to this purple point. So that is okay. Then we will need to open this pin and swap it with this green one. All right, well, let's do it. So, good news, we didn't break the meter yet, but it's not over yet, so still have a chance. Is the circuit diagram from this whiteboard? Well, of course, I designed this board, so I have schematics and PCB file, everything. So I think you need to rephrase your question. it would be easier to just cut header pins in half and bodge the wires into them and move into the proper position of the board. Yes, it would be easier, but then it would also mean that we need to replace that whole header if we want to put the original board. I'm not ready for that yet, so let's turn off. And yeah, we don't need this meter anymore. All we need to do is get our soldering gun and get working on the fix. All right. So first of all, I'll have to remove the connector, I think. Because actually, I have a better idea. Oh, probably better with the micro. I have a better idea. Let's remove the connector first, and then I'll explain that idea in a second. Well, that minus 15 volt is actually there for the purpose. And if you look at the schematics of original A9 board carefully, it will be clear why. It's the same reason why I have minus 15 coming to the new board as well. So I think I'll need a bigger tip than that. So let's replace the tip. So I can use this 4mm chisel. This is one of my favorite tips. Or I can use the big gun. This is 10mm chisel. It's year's part number 102, CDLF10. I think 4mm will be just enough for this purpose. There we go. You'll probably ask, why use so big chisel tip for the small pins and connector? Well, the main reason for that is very simple. With the wider chisel tip, you have much more surface area for the molten solder to contact the pins and transfer heat into the board. This is 6-layer board again. So it would be real easy to just reheat the whole 5 pins, and connector will fall right off. So I can show that on example. So we have same 300 degrees temperature, 300 degrees centigrade, none of this Fahrenheit stuff. Let's get the fume extractor, and then I just make a big solder blob and move it all around, and you will see how easy is it to remove the connector. Same way you could remove the capacitors for recap projects and stuff like that. So there we go. So you give it wiggle, 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 and then little hit, and then it will be out of its way. A little more. Well, sometimes you need to give it a little push. Or more solder. You can always remove excessive solder later. There we go. So connector is out. Still totally usable. No damage to connector. Looks fine. So let me clean the mess on the board. Can use the same trick with the toothpick. So I'll just hit the point and then stick it from the other side, so I get nice open hole. Because remember, we still need to solder the middle pin. Because that is the only pin that is correct. Alright, not too bad. There we go. Well, I do want to test that PX, but I think it will be next year before it makes to me. Thanks to all the virus situation, New Jersey is not going to open anytime soon. Just use the IPA to remove the flux gunk. So the trick is that I'm thinking, because this connector have actually the pin is folding, it's going, the contact is in the other side, then it folds over and goes down, so the pins from the PCB board go through this hole and then contact from the other side. So what I can do, I can just free these corner pins and bend them up, and then I can jump wire the connections in the points on the board. So this should be much easier than alternative way. And obviously I will not fold up the middle pin, because that one is correct. So let's try to do that. And the battery died in the camera. Let's replace that. And new battery, go back to the charge. Hello. How many people watching this? 50 people? Wow, that's a lot. I think that's a record. I didn't think this is that much interesting. Me failing on the $2,000 PCB because of the silly mirrored contact mistake. That's a little bit embarrassing. Okay, so looks like it's bending up. All right. Yep. It's a bit how you're doing. So if we put it back in, come on, there you go. I'll need to, because actually the pin and have some excessive solder, so I'll have to just heat it up and insert when it's hot. There we go. Now reflow the points. So the middle pin is okay. Now I can show what I mean. So now I have these pins, they are completely free. This connector is a little bit wiggle, but that's okay. So now I can connect them to the points I want. I don't know how this connector called in Russian, but in English this is bottom entry connector. So meaning that the connection pins come from the bottom of the board through the board. Bent pin on a small connector, you mean on this one? On this connector? This connector is not connected to anything important. This is actually a completely isolated section, so this part of the circuit not connected to anything on the other end. It's just this is linear regulator. No, this is the temperature sensor, my bad. And this is the I2C EEPROM for the calibration data when I decide to use this board as a standalone reference. So this is nothing to do with any of the precision stuff. So I can connect all these pins together and nothing will happen because this is not used. I think I'll just jump wires to the necessary points to these hanging pins, and that would be it. That's it. So let's do exactly that. So, and this tip is, as you can see, is a little bit too huge for this kind of job. So we'll replace the tip again. I think I'll use this one. Should be nice and adequate. All right. So now back to the connections. Let me see. Yeah. So I'll need to connect the heater. Well, this should be easy enough. So this, I'll need to go to the this point. It's actually even too big. What happened to D30? I have no idea. What happened to D30? I don't even remember what is D30 now. Let's reload it. Yeah, that will do. We just need it to hang on a little bit. There we go. It looks like it's touching this ground exposed line, but it's not. It's kind of hanging right in there, so there is no contact. D30 is for LED. The LED is supposed to be there. Now we can connect second line, which is our minus 15 volts. So that's exactly where it goes. It goes to that resistor. Just a little short right over there. We can actually remove this jumper. Let me get some more solder on the pin. Yeah, this is a silly mistake. Obviously I got this connector. This one is correct, but I didn't realize that this one is mirrored instead of just rotated. So yeah. Let's get that solder thing. Usually I do this under microscope. Okay. It's a little bit how you're doing. That should be good enough. Now we need to have next connection. That would be our power. So it goes to there. I'll need somewhat longer short. That's a little bit too short. That should do. Now we have our input power. Connect it in. And now we have only that open point. I wonder if I need to actually connect that or can leave it without it. Well, let's connect it. I don't remember if it's connected inside the meter for anything. It connects to that R12. So we can have just a short jumper to R12. This is a drive to one of the heaters. There we go. So there you have it. Failure number 1. Always check your connectors and pinouts of them and orientation. Should we try it again? No, that is not gargling refrigerator, that is fume extractor. This thing. It's going the hose, going right the way, well, under the desk, where is the fume extractor. So when I solder, I don't have to get a lung cancer. Can illustrate all the nasty stuff just taken away. I can turn it off now. So let's get back to our meter. Our poor meter. And get everything installed. Back again. I guess I can check that all the signals are correct first. And we can see. So I'll pour power again with the stock reference, measure the voltages. So I want to see my DMM. Thank you very much. So 18 volts. Minus 15. 0. Plus 18. And 8.8. That is heater. Okay. Let's try it. Wiggle, wiggle. Okay. Okay. Let's go. I can replace the lens so you can see what meter says. There you go. All right, we got some samples, no error. Let's measure the voltages. $18 volts. Power is okay. 7.8 minus 15 and 7 volts on the output. Correct. Now we can supply 10 volts and see what happens. Of course, it would not be correct voltage because the output reference voltage is different for this module, and it will take multiple hours to warm up. But we should get something in the ballpark of 10 volts. Let's see. Yep, that's pretty close to 10 volts. At least something is working, so we can recalibrate the meter quickly after maybe 30 minutes or maybe 15 minutes, just to see if it can pass the initial quick checks. We can run the self-test. To see if that passes or not. That's a promising start. How much the ceramic 6-layer board was for the cost price? It was around $800 for 10 boards. So yeah, it's not a cheap board. I think it's about double of the price compared to the normal FR4 PCB 6-layer. Usually I do 4-layer PCBs because they are not that much more expensive than 2 layers, but give so much more flexibility in terms of power layout and overall design layout. So my go-to PCB designs are 4-layer. But actually, in my experience, for the commercial projects, I did up to 16 layers before. It's overall, after you know how to do 2-layer board, everything else is kind of easier because you have more freedom to do. Self-test passed. Okay. That's actually a little bit more promising than I expected, so it's a good sign. So we can probably put the cover back in. I'm a little bit concerned how those tall Keysight resistors, they're a little bit close to the top, but probably still will be okay. Let's try. Yeah, I think it's okay. Didn't hear any screeching or anything. Let's quickly check the noise. For that I can just output higher voltage on the calibrator to get exactly 10 volts on the DMM. So we can estimate that it's super noisy or normal or what's going on. So we can set NPLC 50. And then I'll just increase the voltage on the calibrator. So let's do like that. Okay, one more. And then 8 more. Not too much. Still too much. A little less. I want all 9 digits. Thank you very much. There we go. Little more less. And little less. All right. There we go. So I had to program, let's see what I had in the calibrator. I input 10.028622. So that is, well, you barely can see. That is minus 0.28%, which is okay because LTZ reference is not ultra precise, it's ultra stable. So after you calibrate it, then it will maintain that calibrated output, whatever it is, to the very high stability. And it's okay that the voltage drops a little bit, because it will be dropping quite a bit more due to warm-up, and it may take like around an hour to reach at least 0.3 ppm of the previous level. We can leave it running a little bit, and probably I can answer some questions if anybody have any. So I put the cover back in. All right. So the whole reason why I wanted to change the voltage reference to this quad LTZ reference is I wanted to experiment with the lower noise and answered the question if the lower noise voltage reference in 3458A would actually improve the noise performance of the instrument, or is it actually limited by the ADC or the input front end or the other circuitry inside the meter. Yes, the parts for that reference are selected. The question is, how many layers do typical video cards use these days? Usually high-end cards use from 10 to 14 layers, and middle-class cards I would say 6 to 8 layers, and the low-end cards use 6 layers usually. Okay. What would be the cheapest way of calibration of 6.5 digit 34401A? Bought 3 on eBay. If it's possible, I would do it myself. Well, the tricky part with the calibration of any multimeter is you would need to have a reasonable stable source for all the ranges on all the functions. So yes, you can calibrate, for example, only 10 volt range using the voltref or pentaref module, but you will not be able to calibrate resistance ranges, current ranges, and all that. So usually this is a job for the multifunction calibrator or multiple instruments like the DC calibrator, like maybe EDC MV106, which sometimes can be sold on eBay pretty cheap. And then you will need to have resistance standards for all ranges, like 1 kilo ohm, 100 ohm, 10 kilo ohm, and so on. And for the current ranges, it will be combined, and then you also have AC voltage and AC current. So for the 6.5 digit meters, you usually can find a local calibration lab in the area, and if you request the cheapest calibration they have, they can probably charge you like 100 or 150 US dollars for the full calibration of the whole multimeter and give you a report. So if you ask them nicely, they would be able to help you. That would be probably the cheapest way. Alternative is if you have somebody around in your area with the calibrator and necessary equipment, you can ask them to help you calibrate. But like if you need to ship it to another country or something for that, the shipping cost would make it economically non-reasonable to do that. And also there are different levels of calibrations. You can just get a simple calibration that would say you like, okay, your meter is still in spec, everything is okay, and that's it. That would be cheapest calibration, and more expensive calibration will give you actually what are the errors of the uncertainties of each calibration point and each range, like how much actually your meter deviate from their standard, showing what are the actual results. So you can even apply the correction after you get the meter back. PDVS 2 Mini from Ian Scott Johnston. Yeah, that is very actually nice box. I like it very much, and I'm going to publish some material about it. I have a sample that Ian sent to me. It's one of the pre-production units. I was very impressed with its performance, and it's a nice, capable voltage source, which is very handy to have in the lab. Who was the supplier of the PCB? Well, the supplier of the PCB was Chinese manufacturer. So you can ask your usual go-to PCB manufacturer if they make a Rogers board, and I'm pretty sure they will be happy to make you a board for the extra price premium. Meter looks quite stable. I'm pretty happy with that. But the real test would be to run actual short test, meaning input would be connected to the copper short and measure all the noise from the ADC and from all the function ranges, and compare to the other meters. I mean, to the other 3458As. No, it was neither of those vendors, but it was same great vendor. I probably would be giving away 1 or 2 PCBs, just bare PCB without any components, for the maybe most interesting question in this live stream. So you can ask that later in comments, and let's say the deadline would be end of April, and then I'll ship QVR PCB. You can use just as a souvenir, or design build your own LTZ reference. You don't have to populate all 4, you can just populate 1, and it will be still very nice DC reference. So let's say the deadline is April 30 for the most interesting question about electronics or test equipment or anything related. Well, you don't have to. My Keysight DMM6500 is too noisy. It's questionable because you can use DMM6500 in a ratio mode and use the one LTZ reference against another LTZ reference to compare the noise. Who was the supplier? I don't think that's really important, and I don't want to give the free advertisement for the company. So it's not that I was pretty happy with the result, but I just don't do advertisements. You will never see an advertisement on XDev's project. I'm happy to show off the products that I like and the products that are really impressive, but it wouldn't be an advertisement. Same reason why this YouTube channel is not monetized, because here I just want to share the knowledge and share the tinkering with various instruments that might not be readily available everywhere and everyone. So I just think sharing information online is the one way to say thank you to all the engineers before me who contributed and writing articles and books and do the research and publish all those papers, which I used to learn about precision instruments and all that. So this is just my way to say thank you for all that. Tea or coffee? I like tea. I don't know, something about the smell of coffee is upsetting me, so usually I go for tea. I think we can, I don't see the readings changing that much. I think we can just try the calibration and see if it can pass. Let's do that. So I'll do a really simple calibration. Output exactly 10 volts from calibrator, and then do the 10 kilo ohm from calibrator, and we'll see if meter get nice readings. But before that, the first step is to make put the short. So we can do that. So the purpose of the short calibration is let the meter obtain internal zero that is used for all the voltage, current and resistance functions. So for that I use just piece of copper wire. I can show on the video how it is done. So we have the binding post terminals. Then I just use thick copper wire. I usually have a few runs with the pliers to clean any oxide. It's very important to have nice, fresh, clean copper, because copper oxide is a bad thermal EMF conductor. So let's do a couple more times. Nice and shiny, and then stick into the holes in the post, like so. Then bend it around. You want 4 wires, and then I tighten all the nuts. Do it finger tight. Then exercise the front to rear mechanical switch a couple times, so we get nice clean contact there. And now we can wait a little bit. So right now we are reading around 4 microvolts, and maybe wait a minute or two to let the thermal stabilize, and then we can do the cal 0. While we are waiting, we still can run the self-test again, just to make sure. And what we can do in meanwhile, we can print a nice label showing that this is not your usual standard 3458A. I use a label printer for that. Let's do. Where are my scissors? All right. Self-test passed again. Looking good. Let's put our sticker in. There we go. Looks much better now. So now we can do the 0. Let's do Shift call 0 and then the default password 3458, and now we can press enter and meter performs the 0 null calibration. This takes a little bit of time. Meanwhile, we can verify that our 10 volts indeed is 10 volts from the calibrator. For that, I'll use my reference meter. Connect the 10 volt from the calibrator. Output 10 volt exactly. And perform AKL DCV. This will be our reference value for the calibration. So I can show both of them same time. Video quality is a little bit bad because I use the zoom in function on the DSLR camera. In my engineering, my focus is around, I would say, mixed signal electronics design. Did you get a new front panel for that 3458A? Yes, I did get a new front panel for all of them, all three. It's fairly reasonable priced, so just looks much nicer when you have instrument that please the eye. AKL DCV takes around 140 seconds. So we will see the reading from the reference meter number 3 soon enough. But I think this is pretty much everything I wanted to show today. And probably in next 10 to 15 minutes we can have a wrap the session. But we'll want to wait to see the actual calibration result, if there is no error and if we can get the output of the correct 10 volts. Please, do you know the main difference between 3458A and Fluke 5888? Well, it's completely two different instruments. And price difference, brand new 3458A from Keysight in base configuration is around 11K. You can actually order it online on the Keysight's website, and it's already shipping, so you can buy anytime you want. And Fluke 8588 it cost around 17,000, and it's completely different instrument. So Fluke 8588 more tailored for metrology use. It have more functionality. But if you want ultimate DCV performance, then 3458A, in my opinion, is still much better. So it depends on what's your application and what's your purposes. Yeah. For resistance transfers and for work with the RF, for example, Fluke 8588 probably will be better because it have better resistance functionality, and also have the port for the Rhodes-Schwarz power sensors, so you can calibrate those and use those sensors externally together with the meter to calibrate your power meters and other RF equipment. Alright, so 0 is finished. We get a nice 0.2 microvolts or thereabout. So we can do 10 volt calibration right now. We remove the short from the instrument and connect our 10 volts, which we measured on the reference meter. So it's, let's say it's around 10 volts exactly. So that's 10 with the almost, I'd say, we can just program 10 volts. That error is negligible in the end. So I'll disconnect this, connect in here. So we should get our, this is our guard. And we can connect the sense as well for the resistance step. There we go. I'll move the cable a little. Yep. We get our 997 something. So now we can call 10 0 0. Well, you can enter the full value, but it doesn't matter because we just have 10 0 0 58, same password. Now wait a little bit to let the thermals equalize when we replace the connections. And again, I don't recommend to do the calibration at least a couple days before you left meter powered on. So normally it would take a couple days for meter to warm up to nice and stable conditions, and after that you can do the calibration. Otherwise, for example, right now we calibrate, but the reference might still be drifting like few ppms over a couple hours in the worst case, and then you will have to recalibrate again because you didn't wait enough till the meter gets stable. So you don't want to do anything fast with this kind of equipment. Yep, calibration just like wine. The longer the better. But for these purposes, we don't really care about long-term stability. This is just experiment. And obviously you wouldn't be doing this kind of experiments on your only or your primary 3458A reference multimeter in your lab. Because now even if I get better, in theory, better voltage stability or noise, I probably ruined resistance functionality completely, because all the extra heat dumped from new module into components right under it, which are part of the resistance current source. So probably I improved something, but made it worse in many other important areas. Again, in this case I don't care, because this is not my primary meter. It's just a learning experience. Just meaning that you need to know what you're doing and what are your goals to achieve. So this step takes around same 3 minutes. Then we can do 10 kilo ohm calibration. And actually for my primary meters, like those two, I didn't use the calibrator for the calibration output, but I used my standard that is located right over there, that black box with the blue label primary reference. I just got it calibrated a couple months ago by Traceable Calibration Lab, and I use that as my primary 10 volt reference. And for resistance reference, I obviously use the best 10 kilo ohm resistor in the world, that is ESI SR104. Right there you can see test wires coming out of it. Then I use the nanovolt meter to compare the voltages between the calibrator and DMM for all the ranges other than 10 volt. And for resistance calibration on the Fluke calibrators, I used my primary reference for resistance, this guy. This is a prototype from Fluke Secret Labs. It's Fluke SL935. It has 1 ohm and 10 kilo ohm outputs, and also calibrated by Traceable Labs multiple times, both in US and also by Taiwan National Measurement Laboratory. Alright, we got our calibration done for 10 volts. And look at that. That's pretty close to 10. Not perfectly 10, but I'd say close enough. And just a couple least significant digits up and down. Look promising so far. Let's do the 10 kilo ohm. So I'll switch the calibrator to output 10 kilo ohm. Oh. So I can program 10 kilo ohm 4-wire operate. So this is the value from the calibrator. And then we can enter that value into our calibration. So we can first measure as it is. And we select correct range. Obviously it will be way off because all the currents and everything is different. So offset compensation, we need that. Then we need to have delay, because the error from the cable can corrupt our delay 1 second, corrupt our accuracy. So that should be closer to correct reading. And now we can wait a little bit and then do the final step for 10 kilo ohm calibration. This is the longest step, because it's also doing all the verification for 999 805. Oh, should be dot 805 and the password 3458A. So this step also do the calibration and internal adjustment for all the current sources. So it will also calibrate current function. All right, let's go. According to calibration results, my SAR104 over the last 6 years changed its output resistance less than 0.1 ppm. So over 6 years, that is a remarkable result, especially considering that resistor age is more than 40 years. I would say maintaining sub ppm accuracy for resistance is actually easier than maintaining sub ppm accuracy for voltage. Because for voltages, unless you have a quantum standard, you're always dealing with the drift and calculating all the factors to factor that in. So if anybody have metrology related questions, you always can reach me out in comment section in the video, or through the email team email sign xdevs.com, or on the EEV blog forum, especially in metrology section. So feel free to contact and ask your questions. The whole reason why I'm doing this video is to share the experience and some knowledge. So far, this experiment on replacing reference in 3458A seems somewhat successful. Let's not mention the botched connector. We all do mistakes. That's the normal process of learning. And I'll be testing it a little bit more in detail, and probably in a couple weeks we'll publish results online, so we all can see if this have any positive improvement, or it was all just for everything, just for nothing. What is my opinion on Fluke 5450A? Well, this is a great instrument, and if it's properly maintained, like you said, clean relays, make sure the leakage is maintained under control, I think it's actually better resistance standard than any other calibrator available, including 5720 and 5730A. I am still yet to do the full work on mine 5458, but I'll do it sometime, probably during some other video later this year. I don't have much confidence in Transmile, to be honest. Based on the internal design and how they build the instruments, at least the older ones, that does not imply much confidence in metrology parameters either. And the bigger reason is that all the critical important short-term stability factors and specifications somehow forgotten or not mentioned in the manuals and specifications they publish. I wonder why. Maybe because they have to hide something? I'm not sure. I didn't personally had any Transmile instruments, so I cannot be 100% sure, but based on the test results I've seen by friends, it wasn't a real competitor to the big names like Keysight, Fluke, Keithley, and so on. Unfortunately, that cool looking 8508 is only cool looking but not cool working. So that is work in progress. And let's keep it at that. So right now it's doing the calibration for current 0, DCI, DC current, 1 microamp range. I think it's about halfway in already. And the battery and camera are about to die soon. But that's all right, we're almost done here. Two hours, 30 minutes. I don't have short live streams, eh? Okay, still a little bit more. Well, ESI is not is a part of EAT now, because EAT bought them. So now you have to look at EAT lineup, and IAT is still making the instruments and products from ESI line, but I don't have any experience with the newer stuff, because pretty much everything I have in the lab is from eBay or friends or other sources from secondary market. Alright, so resistance calibration is finished, and this is value we have on the calibrator, pretty close, 999,812, and on calibrator we have 999,805. So 812, that would be just, let's say, 0.7 ppm high. So completely acceptable error. Let's do the other ranges, like 100 millivolt, 1 volt, to see if the reading is still good. We can do 1 volt. We can reset the delay because we don't need it anymore. Delay 0. Output 1 volt. Let me get... Okay, that is somewhat big error. Let's do reversal. That meaning negative 1 volt. Okay. Let's do a now with the fixed range. So this is 0 volts. Let's select 1 volt. Do the now. We need to remove the offset. Do the same again. 1. Okay, somewhat better. Now we can do the reverse. Okay. We can try 100 millivolts. Let's go down one range. That's our 100 millivolts, negative. Okay, somewhat close. Let's do 10 volt again. So it went a little bit down, but again, like probably reference drifted a little bit, still warming up. Negative 10 volts. So you see it's around like the same 0.2 down, and here is 0.2 up. That is not too bad. Let's try 100 volts. to operate twice. $100. You can try negative. Okay. You can try 1 kilovolt. Little bit bigger error. Negative. Okay, well, we'll have to do more detailed testing offline. We can check also current. Let's do 1 milliamp. Auxiliary output. So right now there is no current supplied from calibrator. Or it's somewhat... oh, this is... I need to remove the math, because math is not functional dependent. Let's supply 1 milliamp. Okay, almost perfect 1 milliamp. No problems. Negative. Little worse, but not too bad. We can try AC voltage as well. Let's say 10 volts, 1 kilohertz. ACV. Set ACV sync. So this should be 10 volts or there around. It's a little bit too low. Yeah, I think that is too low. We can check that with another 3458A. This actually cable is suboptimal for AC voltage. So I connected same settings. Same settings on the calibrator. 10 volts. 1 kilohertz. Yeah, this is how it should be. We can reset the settings on the experimental one, just to make sure. Reset. ACV sync. Okay, there was some glitch with the connection, but thanks everyone for watching, and we'll see you in the next video.